Okay, welcome to the P1 revision video. I'm just going to get started with this straight away to make the video as short as possible. So, getting started. So this is what we're going to be doing is first of all, we're going to be covering heat and temperature. Okay, and believe it or not, they are two different things. So, starting off, which one has the highest temperature? Oh god, sorry, 1 second. Yeah, which one has the highest temperature out of the coffee and the swimming pool? Okay, obviously, yeah, it's the coffee, probably about 80 degrees, and the swimming pool, let's just say 10 degrees. Okay, now, if I ask you this question, which one has more heat energy? Okay, now, some people would have thought coffee has more heat energy, but it doesn't. Okay, the swimming pool would have more heat energy, even though the coffee is at higher temperature. Why? Because the coffee has fewer atoms, which all carry more energy each, but okay, all the atoms in the swimming pool, okay, would be carrying a small amount of energy, but there are more of them. So in total, the swimming pool has more heat energy. Okay, so what is temperature measured in? Well, that's measured in degrees Celsius. And what is heat measured in? That is measured in joules. Okay, right now, heat direction. This is the next bit. So if you open the door to your house on a cold day, do you let the cold in or do you let the heat out? Why? Well, heat always goes from hot to cold. Okay, so there's always a common misconception when people say, oh, you're letting the cold in. That's not what's happening. What's happening is you're letting the heat from the house out. Okay, heat always moves from hot to cold. Okay, like I've already said here, the energy in the atom spreads out to all the neighbouring atoms, etc. Okay, now moving on to changes of state. Okay, this is some basic year 7 stuff. Looking at a solid, okay, when it's heated up, okay, it's going to go through the melting process, and that's going to turn into a liquid, and then you heat the liquid up, it's going to evaporate and turn into a gas. And obviously the other way around, when the gas can turn back into liquid, it's going to condense, and when the liquid's going to turn back into solid, it's going to be freezing. Why are we covering a year 7 topic? Again, because we need to know a little bit about this. Okay, this is showing changes of state, and when you heat up let's just imagine you're heating up like a beaker of ice. Okay, the ice is obviously going to be solid. Okay, and you're going to start heating the ice up, and the temperature is going to start to rise. Okay, until you get to this point. Okay, now you notice that this is temperature, by the way, and this is time, and you notice that the temperature just stops increasing. So why does the temperature go flat here? Okay, even though that you're still adding heat energy? Well, the reason being is because all the energy, okay, is going into melting the ice as opposed to making the temperature increase. So all of this point is all the ice melting. Okay, when all the ice is melted, okay, and turned into a liquid, the temperature will start to rise. Okay, now when the temperature has risen again, okay, the temperature is going to stop rising when the liquid is started to turn into a gas, until it has all the energy to turn all the liquid into a gas, which is what's happening here. Then the temperature will start to rise. Okay, this is latent heat. Okay, now the word latent means hidden. Okay, because all the energy here at this bit where it's changing state is going towards, well, changing the state of the liquid, okay, or the solid. Okay, so here's a solid, all the solid is melting, so that's where the energy goes. When all of it's turned into a liquid, it starts to increase. Now when the liquid's trying to turn into a gas, until all the liquid has turned into a gas, the temperature won't rise, but when all the liquid has turned into a gas, it will start to rise. Okay, so like I said, it's latent heat, and it's the heat required to change state without a change of temperature. Okay, now moving to specific heat capacity. Now, you've all heard of specific heat capacity. Now, you need to know the definition of it. Okay, now the definition is this. Okay, the definition is, okay, specific heat capacity of a substance is the amount of energy needed to change the temperature of 1 kilogram of a substance by 1 degrees. Now, specific heat is always about 1 kilogram, okay, making the temperature rise by 1 degree. Okay, now what you need to know is that different substances have different specific heat capacities. Okay, now on the next table, this shows, this one is in joules. Okay, this one shows the amount of energy needed for water. Okay, so these numbers might not mean anything to you, but if I say it like this, like I said here, it's the amount of energy needed to turn 1 kilogram of a substance by 1 degrees. So this is 1 kilogram of water, making it rise by 1 degrees is going to take 4,181 joules. Okay, if you ever see it written in the exam, it will probably say 4.2 kilojoules. Okay, now of oxygen, yeah, it takes 918 joules to make 1 kilogram of oxygen rise by 1 degree, and lead, which is a metal, okay, takes 128 joules to turn 1 kilogram of a substance by 1 degree. So you all know that metals conduct heat really well, so they tend to have a very, very low specific heat capacity, i.e. it takes less energy to make the temperature of 1 kilogram of that substance to rise by 1 degree. Okay, now you need to be able to calculate that. Okay, SHC, specific heat capacity. Now let's imagine if you had let's just say you had 5 kilograms of water and you wanted to make it rise by, let's say, 10 degrees. Okay, so what you would do is you need to calculate how much energy is required to do that. So it's 5 kilograms of water, so it's 5 kgs, times by the specific heat capacity, which I think is going to be 4.2 in this case. Okay, and then multiplied by the temperature change, which was 10. Okay. Just a side note to this, okay, it won't just give you the temperature change. It might say that the temperature rises from 20 degrees to 27 degrees. Now, some of my students just use the number 27, and that would be wrong, wouldn't it? Because it's the temperature change. So what you would do is you'd start from 20 degrees, take away off that 27, which leaves the temperature change of 7 degrees. Okay, so it'd be 5 times 4.2 times 7. Okay. Now, this also might be how the temperature is written, the equation is written. Amount of energy needed to raise the temperature of 1 kilogram of material by 1 degree. Energy, mass in kilograms. Specific heat capacity, like I said, most commonly will give you in joules per kilogram on change of temperature. They will give you the units for it. Okay, sometimes it's in joules, sometimes it's in kilojoules. Okay, right now. Specific latent heat. Okay, now that, like I said, let's go back to this graph over here. Okay, you see the amount, all the energy that we're given this to be able to turn it from a solid into a liquid. Well, you can also have an equation for that. Okay, now that's called the specific latent heat of a substance, and it's a measure of how much heat energy is needed to melt or boil it. Okay, and it's 1 kilogram of that substance. And again, just like specific heat, different substances have different specific latent heats. Okay, so the equation for this is the mass of the substance. Okay, this is quite an easy one, multiplied by specific heat, specific latent heat. Okay, so let's say, for example, if you have 5 kilograms of a substance and it will give you the specific latent heat, you just multiply them by each other. Yeah, so specific latent heat relates to this graph over here. Okay, right there. Okay, or right there. This is when it's melting. This is when it's going to be turning. This is going to be its boiling bit. Okay. Now, moving on. Keeping homes warm. Okay, now, we all know heat energy can be lost from homes in different places. You can lose it from the roof, you can lose it from the windows, you can lose it from the walls, you can lose it from the floor. Okay, now, what you need to know is ways of reducing these heat losses. Okay, but not only knowing how we can reduce those heat losses, you need to know how that heat loss happens when you're discussing these three, which is conduction, convection, and radiation. So let's just look at each one of those in turn before we look at how heat can be saved from the house. First of all, conduction. Conduction happens in solids. Okay, now this is obviously a diagram showing that some a metal being heated. Now what's going to happen is these atoms are going to start vibrating first as they gain some heat energy, and they're going to pass the energy on to the neighbouring atoms, and they're going to start vibrating. So this one's going to start vibrating first, and then it's going to pass the energy on to this one, then it's going to pass the energy on to this one, and and so forth. This one onto that one, maybe onto that one, and that one, and that one, because they're all touching, aren't they? Okay, and eventually all the heat will start getting passed on, and it will start moving through the actual metal. Okay, now that is conduction. Okay, so it's about heat energy, about the atoms vibrating and passing the energy on to the neighbouring atoms. Okay, now obviously conduction happens quicker in metals. Okay, now you don't need to know a lot about why. So if you can just remember that conduction happens quicker in metals because of something called electrons. Now electrons are something that just orbit around the metal atoms, and they help pass the heat energy on. So they're really, really tiny bits, okay, just surrounding the metal, and they help pass the energy on. So if you're ever talking about metals and conduction, just remember electrons help pass that heat on to the next atom. Okay? Now, convection. Convection happens in two things. Convection happens in air, okay, and convection also happens in liquid. Okay, now you need to know a little bit about how convection actually happens. Okay, so let's just talk about it from this point of view first. Okay, imagine a saucepan with some water in it. Okay, heat is obviously going to be heating up at the bottom. Okay, so as these atoms get hotter, okay, they're going to start to vibrate a little bit more. So imagine in this region over here, let's just imagine this region over here. Let's imagine that you've got loads of atoms here. Okay, how do I select these? So bear with me a second. Ah, there we go. So let's just imagine that we've got a load of atoms, okay, right here. Obviously they're going to be in liquid form. And what's going to happen is as they get heated up, let's just imagine as this one gets heated up, this one's going to start vibrating more. These little lines, and we're trying to signify that the fact that they're vibrating. Okay, these atoms are going to start vibrating because they're absorbing more heat energy. And what they're going to happen is they're going to start moving, and so they're going to space out a little bit more. Okay, because they're moving. Just like you guys, if you're in a crowded room and you start swaying from side to side, you'd need more space, wouldn't you? Okay, now what happens is that the space in between these atoms would increase, okay, so the density, okay, would go lower, okay, you'd be a change in density. This material would become less dense, okay, so, which means it will take up more space, okay, and if these atoms have less, lower their density, it means that they're going to rise. Okay, so when they rise, they'll go to the top of the pan. Okay, and obviously, if these atoms have moved out of the way, then their space would need to be occupied by newer atoms. Okay, and these atoms would move in their place. Okay, and then they would start to get heated, and they would rise to the top. Not sure if that's a brilliant explanation, so I think this may help you explain that. So you can see the heating element in the kettle. The atoms have started to gain energy, lose their density, and they would start to rise. Okay, the heated water becomes expanded. Okay, the key to understanding convection is it's about density. Okay, so like it says here, the heated water expands and becomes less dense, and so it rises to the top, and that is replaced by cooler water, okay, by the sides of it. Okay, and eventually, because it's further away from the heat source, it would cool down and come back down, and they would start making this sort of circular movement, and that is what's known as a convection current. Okay, so it's really understanding that in terms of convection. Okay, and so obviously as the hotter it gets, it will start, circulating that little bit hotter each time and a little bit quicker, etc. Okay, now that explanation can also be used when we're trying to understand air. Okay, so if you've got this radiator, obviously the air near it is going to get hotter. Okay, it's going to become less dense, and it's going to rise, and that's going to be replaced by cooler air, which is then going to go near the radiator, get heated, and then start to rise, and that's going to be a convection current. I've seen rooms where the heating elements are right at the top of the room. Okay, that to me doesn't ever make any sense. Okay, because all that would do is just going to heat the air right at the top of the room, and keep the air less dense, and so the hot air would stay up and the colder air would be down here. It doesn't make sense to me. So that's why heaters, radiators are always at the bottom of the room, where they heat up the air gets less dense, rises, replaced by cooler air which moves in, and then that air obviously gets heated up, and you set up a convection current, like a nice little circle going on. Okay, which is why you shouldn't really block radiators, because obviously air needs to get to them. Okay, right, so that was convection. Okay, so like I said, the explanation with that is that the liquid or the gas becomes less dense than the liquid in colder areas, so it rises. Okay, that's the real key bit, in that the liquid gets hot, okay, becomes less dense, okay, and then it begins to rise, okay, into the colder areas. The denser cold liquid then falls into the warm areas, and this way the convection current takes place. Okay, now radiation. Now, the thing you need to know about radiation is that heat is transferred by infrared radiation, but it's not like conduction and it's not like convection, because both of these need particles. Okay, infrared radiation is a type of electromagnetic radiation, and that involves waves and doesn't need any particles. Okay, and that is why radiation can work in a vacuum. A vacuum means is when there's no particles, just like in space, and that's how the sun is able to heat us from all those millions of miles away. Okay, so it's radiation, infrared radiation, that travels from the sun and makes its way towards us. Okay, and that's how radiation works. Now, the thing you need to know about radiation is radiation can... different objects, when objects are hot, okay, they emit infrared radiation, okay, but also objects can also absorb infrared radiation. Now, what you need to know is that black dull objects are the best emitters and absorbers, and shiny white are the worst absorbers and emitters. Okay, now this probably makes more sense if we have this little experiment over here. Okay, so if we get this box, okay, and we fill it up with water, and then we see how much infrared radiation is going to be emitted by all the sides. Okay, so this is obviously a, let's just do it with the silver side first. So this is the silver side, the starting temperature is 20 degrees. Let's just see, put the water in, what temperature does it get to? So it's 80 degrees inside there, and eventually it's going to get to 28 degrees. Let's just very quickly do the same thing with matte black, rather than going through the whole thing. Come on. Okay, and let's just look at it. Water goes in, again it will be at 80 degrees, and it will rise to 42. Okay, so obviously you can see that the matte black is the best emitter. Okay, it emits most of the infrared radiation. Okay, obviously the shiny black could come second. Okay, and then I'd guess white would be the next one. Let's have a look what white would come out as. Okay, white comes out at 32. Let's just do the next one. Okay, shiny black. Obviously, it will come just below 42, maybe 38, I'm going to guess. Let's have a look. Alright, with 38. Come on, 38. How did I know that? Wow, a genius. Now, I've seen this before, I'm joking. Okay, so that was that. Okay, so that is showing that that's going to be the best emitter. Okay, matte black, best emitter, then followed by shiny black, then followed by white, and then silver. Obviously, silver is very reflective. Okay, so, like I says, best emitter, matte black, worst emitters, silver and white. Okay, let's move on. This is exactly the same experiment. Okay, but now what we're doing instead is that we cover something and see how much it emits. Okay, now the numbers for this are exactly the same. The matte black is going to emit 42 degrees. Okay, alright, and then is exactly the same as the last one, but instead now it's emitting. Okay, oh no, sorry, it's not emitting, it's absorbing. This one is absorbing. So this is obviously the heater, and it's heating up the water, and obviously it absorbs the most. So the experiment before was about how much it emits. This one is about how much it absorbs. Okay, which is exactly the same. Okay, right, now moving on. Okay, ways to insulate the house. Right, so carpets, double glazing, triple glazing, loft insulation, draft proofing, foil behind the radiators, cavity wall with foam, cavity walls without foam, which are all the ways in how you can insulate the home. Now, you need to know a little bit about how all of these things work. Okay, so heat loss through the windows, okay, is reduced by double glazing. Now, the special windows have air or a vacuum. Remember, vacuum contains no particles, and it's because air is a poor conductor of heat, okay, when it's trapped. Okay, so this basically, when double glazing stops conduction. Okay, now heat loss through the walls is also reduced by cavity wall insulation, and so you put a material. So cavity walls basically are when you have two layers of bricks and there's some air in between there. Okay, now what that's supposed to do is reduce conduction. Okay, but the problem is you still get air moving between the walls. Okay, and so you get convection current. So heat loss is through convection, which moves up and down. So if you imagine that with a cavity wall, okay, this is one layer of bricks, okay, and this is another layer of bricks, okay, you still get a layer of convection currents going here, okay, so obviously it stops conduction, okay, but if you've got a gap there, right, it stops conduction, but you still get a convection current. So what you do instead is you fill it up with foam, okay, right through the middle. Now what foam is like a solid, but with spaces of air between it, and trapped air, okay, is a very, very good insulator, okay, and it'll stop the convection current from happening, okay. So obviously this stops carpets will stop conduction, so will double glazing and triple glazing. Loft insulation will stop conduction. Draft proofing will stop convection, because you won't get, so underneath the doors you can get like draft excluders, and they stop convection currents because obviously air can move. So any movement of air talks about convection. Now fall behind the radiators, okay, that will stop conduction from happening, because the radiators, because they're just nailed to the wall, they're attached to the wall, they will start heating up the wall, won't they? Okay, which obviously will be conduction. But if you put like a layer of foil behind it, it will reflect the heat back into the house, and this will stop conduction. Okay, cavity wall with foam, let's just talk about cavity wall without foam. That will stop conduction, but you'll still get convection happening, okay, alright, but this will stop conduction, and it will also stop convection, okay, it will actually stop both of those, alright, okay, so that is that, so that's ways to insulate the home. Okay, so the heat loss through the house can be stopped by putting a layer of loft insulation as well, which works just like cavity wall insulation. Now, payback time. Okay, now payback time is the amount of, imagine that you've just spent some money putting in some, I don't know, double glazing. Okay, it's the amount of time that it takes to actually pay back the cost of what it cost you to install it in the first place by how much you save per year. Okay, so the equation is the cost of insulation divided by the yearly savings. So for example, if you bought draft excluders which cost you £80, okay, that would be the cost of insulation. Okay, so you'd put £80 right here, okay, £80, alright, and if it saved you £20 per year, okay, you would divide them up by each other. So how long would it take to pay back the money? Well, you can work that out in your head, okay, so it's 4 years. Okay, because you save £20 a year, £20 a year, so 4 years, you'll pay back the cost of your draft excluders. Now, you may be thinking, well, I'll just work that out in my head, but it's not always so easy. So this cost of insulation might be like £2,766, and it saves £87 a year. You're not going to work that in your head. So you just divide the cost of insulation, which is 2,766, divided by, well, I can't remember what number I said, 87. It will give you a number which is the number of years. Okay, and that is your payback time. Okay, efficiency. Now, efficiency, okay, looks at how efficient something is. And when I say how efficient something is, I mean that depending on how much energy you put in, how much energy goes into the useful thing that you are trying to create. Okay, it talks about wasting as little energy as possible. So if something is very, very efficient, okay, it wastes very little energy. Okay, if something is not very efficient, that means it wastes a lot of energy. So for example, a light bulb. Okay, if you supply it with 120 joules of energy and only 10 joules of energy is converted to light, what is its efficiency? Well, it's going to be 10, yeah, divided by 120, because this is the equation for it. Useful energy, okay, which was 10 joules because it's trying to make light, isn't it? Okay, divided by the total energy, which is 120. So 10 over 120. Okay, so it's 10 divided by 120 gives you 12%. Okay, by the way, 10 divided by 120, and it's multiplied by 100 to get the percentage. Okay, don't forget that. Okay, and that will give you the percentage efficiency. Now, efficiency can also be represented in a diagram, okay, called a Sankey diagram. Now, you may need to draw a Sankey diagram, but it will give you like a graph paper. So, for example, if it's supplied with 100 joules and it's a graph paper, you probably want to use 10 squares for this, okay? And all the useful energy points forward, it points towards the right, Okay, so in this case it was 10 joules going forward, so that's the useful energy, and it wastes, okay, 90 joules as heat energy. Okay, most appliances do waste quite a lot in heat, and that is pointing down. Okay, so if you're trying to draw this, I'd probably draw 9 squares across. Okay, 1 square for that, okay, and 10 squares for that, so it's all in ratio of each other. Okay, now you compare this Sankey diagram with this one over here, still supplied with 100 joules of energy, but instead now it converts 70, okay, into light and only weighs 25. Okay, and you can see just by a diagram that which one is more efficient. This wastes a lot, okay, and this wastes very little. This sends very little useful energy forward, and this one makes a lot of useful energy. Okay, so that is what is called a Sankey diagram, and it's all relating back to efficiency. Okay, now talking about waves. Okay, now you need to know the structure of a wave. Okay, well, you need to know about labeling a wave. Okay, now first bit to start off is the top of the wave. This is the easiest. Now it's either called a crest, okay, or it's known as a peak. Okay, now the bottom of the waves, okay, now you call them troughs. Okay, just right there, those are all troughs. Okay, now the amplitude of the wave is from the middle point of the wave to the top. That is the amplitude. Okay, so we've talked about 3 things. We've talked about the crest or the peak, trough, and the amplitude. Now, wavelength, you can measure wavelength in different places. It's got to be from the same point of the wave to the next point of the same wave. Okay, so in this case that they've done it from the top of this wave to the next top of this wave. Okay, you don't have to do it from there. You can do it from the bottom of the wave to the next part of the bottom of the wave. That is also one wavelength. Okay, or you can do it from this side, okay, all the way to the next bit where it's going down. Okay, or you can do it from the top of this wave. Is this getting a little bit confusing? To the next part of this wave. Okay, there are different places in which you can measure the wavelength for it. Okay, now wave speed. Okay, now wave speed is really easy, guys. It's just frequency multiplied by wavelength. The only place, and they're going to trip you up with this in the foundation tier, because you don't have to rearrange the equation, is that they may change the units. Okay, they might give you the answer in megahertz, okay, or they might not give you the answer in meters. Okay, so just bear that in mind. Okay, so usually it's going to be hertz multiplied. It's going to be hertz for the frequency. Okay, or it's going to be meters for the waves. Okay, change it if you get a question. Change it to hertz or change it to meters. If I give you in centimeters, change it to meters. Okay, unless it tends to, at the end of the question, it will give you the units. Okay, so I'll have all the lines there for what to write down, and then it might give you the units at the end. So just bear that in mind. Okay, it's just frequency times wavelengths. Pay attention to the units that it gives you, and the wave speed is measured in. It's just a speed, so it's meters per second. Okay, meters per second. Okay, meters per second. Okay, or it may be written like this. I doubt it would be written like this. Okay, it tends to be m/s. Okay, diffraction. Now, diffraction is all about how a wave spreads out for a gap. Now, you can see that this wave is moving in this direction, yes? Okay, now this gap is very big, isn't it? And so the amount of diffraction is how the wave bends. And you can see, because the gap is so big, the wave isn't really bending that much, is it? Okay, you can see that right there. It's not bending very much at all. Okay, whereas in this wave, the gap is tiny. Can you see that? And now, which one shows the biggest diffraction? Well, the smaller the gap, okay, the bigger the amount of diffraction. You can see diffraction talks about how much the wave is actually bending. Now, this wave is bending a considerable amount because the gap, okay, is very, very small. Now, basically, the key to remember is, you see this is the wavelength from this bit of the wave to the next bit. If the gap is bigger than the wavelength, okay, you're not going to get very much diffraction. If the gap is about the same size of the wavelength, so the wavelength is that and the gap is about that, they're roughly about the same size, that will give you the maximum amount of diffraction. Okay, that's what you really need to get. So if you ever see a question like this and there's a reasonably small gap, show the diffraction like this. If it's a very big gap, show a little bit of diffraction. That's what you really want to be looking at. Okay, Now, refraction. I know this can get a little bit confusing, diffraction, refraction, but it's quite easy. You can see, if you look at the straw in it, you can see it in different places, can't you? Okay, now refraction is all about light bending when it goes from a less dense medium like air into a more dense medium like water or glass. Okay, so that was for water, and it's showing some diffraction. So light, as it enters the medium, it bends. Okay, which is why you see the straw in two different places. Now you can see this through glass. You can see how the light is bending as it goes into a more dense medium, like glass. Okay, so this is obviously, this is air and this is glass, and it's bending. Okay, so it always bends. Now the key, what you need to know is that, you know where the light goes into the glass. Okay, you draw a line which is completely perpendicular to the entrance of the light, and as the light source goes into the glass block, it bends towards this line. This line is called the normal. Okay, I don't know if I can write this with my mouse. This is pretty terrible, but that's not great, but is bending towards a normal. Can you see that? So it's bending towards a normal, and as it leaves a more dense medium, it bends away from the normal. You can see that bending away from the normal. So like I've written here, this shows bending of light when it goes from a less dense medium like air, okay, right there, into a more dense medium like glass or water. Yeah, this is refraction. This was diffraction. Easy peasy. Reflection. Sorry, one second. Right, so reflection, really easy. You have the incident ray, which is the original light that actually shines on the surface, which is the mirror, and then you get the reflected ray. The angle of incidence is equal to the angle of reflection. So if it comes in at this angle, okay, it's obviously going to leave at the same angle. That is terrible drawing. Okay, but you get my point. So I equals R. Angle of incidence equals to the angle of reflection. And this line, this dotted line that goes in the middle, is called the normal. Okay? Easy squeezy. Okay, now moving on to the electromagnetic spectrum. Now, electromagnetic spectrum is really easy. First of all, you have to know that all of these in order. So you have to know radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, and gamma rays. Now, if I were you, okay, I would come up with your own mnemonic, okay, because you need to know these in order. Okay, so what they might do is have some of these, but some of these might be missing. So just think to yourself, I need to come up with a phrase that goes R, M, I, V, U, X, and G. My class came up with Real Madrid is very unique, and I can't remember what they came up with, the X and the G. I can't remember now, but that's how they started. Real Madrid is very unique. Okay, and maybe you could just put the XG at the end, I don't know. But anyway, that does help you remember the order. Now, what you also need to know is that, can you see how the waves are a lot more spaced out here and begin to get tighter up here? Well, remember, if you remember from the other video, the peak of the wave to this one, yeah, is the wavelength, isn't it? Okay. Now you'll notice that as you go down the electromagnetic spectrum, the wavelength becomes smaller. Okay. Now you can see the wavelength getting smaller because the waves are carrying more energy. Now what you'll also notice is if the wavelength is getting smaller, you get more waves passing every point through each second. So the frequency, okay, is getting higher. So this is the symbol for wavelength, and you know that the wavelength, as the electromagnetic spectrum goes from left to right, the wavelength gets smaller, okay, but the frequency, okay, gets higher. Okay, and you can see that right there. So that's the electromagnetic spectrum. So we just need to look at these in a little bit more detail in the next few slides coming up. Right, infrared cookery. Is cookery a word? I don't know. I have a friend called Cookery. Anyway, infrared cooking heats food by cooking the outside first. The particles in the food then transfer the heat by conduction. Okay, the outside of the food gets cooked first, and the problem with this is that the inside of the food does not always get cooked. Okay, so infrared waves, light for example, putting it in underneath the grill, okay, is going to the infrared waves are going to hit the outside of the food first, and then the atoms are going to start vibrating, and they're going to pass on the energy by conduction throughout the rest of the food, and then eventually the inside of the food will become cooked. Okay, infrared is also used in remote controls. Now you need to know that. Okay, now you compare that. What you need to do is you need to compare that with microwave cooking. So looking back to the electromagnetic spectrum, we're comparing microwaves and infrared now. Okay, so in microwaves it's slightly different. Okay, microwaves cook the food by the water and the fat molecules. You must remember, microwaves cook with the water and the fat molecules absorbing the energy from the microwaves, and then when those water and fat molecules start absorbing the energy and start vibrating, they start then passing that energy on to the rest of the food, and so the rest of the food is then cooked on by conduction. Okay, right, by conduction. Okay, and maybe convection if it's a liquid. Okay, now the other thing you need to know about microwaves is that they can pass through glass and plastic. Okay, must remember that. Must remember that they cook by absorbing by the water molecules and fat molecules absorbing the microwave radiation, passing the food on by conduction or convection if it's a liquid, and it can pass through glass and liquid. They're the really key points. Okay, thing you need to also know about microwaves is we talked about infrared waves are used in remote controls. Well, another communication forms of microwaves are the fact they're used in mobile phone communications, which is why the mobile phones heat up your brain just a little bit, and I've done a lot of research into it, but the amount that they actually heat up your brain is very, very small. We're talking about like maybe 5 joules or something along the lines of that. The thing you need to know about microwaves is that you need to be in the line of sight. So if this little tower is the transmitter for microwaves, you need to be here. Okay, this is in the line of sight with your mobile phone in your ear. So that's you with your mobile phone. That's a big mobile phone, but you need to be in the line of sight. If you're not in the line of sight, for example, if the transmitter is here and you being the receiver is right here, okay, that's a horrible drawing, but there's a building in the way, that is not the line of sight. Okay, so you will not receive the communication. Okay, so that is that. Alright, so just comparing infrared heating and microwave cooking, like I said, infrared heats the outside first and it travels by conduction. Microwaves, the water and fat molecules, like it says here, water and fat absorb the energy and the kinetic energy increases and it passes on the food by conduction. Okay, so both of them cook by conduction. Okay, there is that. Total internal reflection, so carry on looking at waves, etc. Now, you notice that if you shine a light straight, this is, by the way, this is a glass, okay, if you shine the light source through it at 0 angle, so it's straight through, there's no angle to it, it goes straight through. As you start bending the light source, okay, you can see how the light started to bend. Okay, you can see that, but the light is coming out of the glass block. You can see that, can't you? Yeah? So it's coming out of the glass block here, here, and here. Okay, so when it's at a certain angle, so when the angle isn't too great, the light source will actually come out and some will be reflected in. Can you see how a little bit is reflected here, a little bit is reflected here, back into the glass, a little bit is reflected here. But there becomes a point where the angle is so steep, okay, that no light is actually reflected out. Can you see that? Okay, no light escapes the glass block. There's no light here at all. All of it is reflected back in. Okay, now that is called total internal reflection. Okay, you can see why it's called total internal reflection. Here, only some of it's being reflected back in and most of it's coming out. Okay, but you get to a certain angle, all of it's being reflected back in. So it's total. It's totally internally reflected. Okay, so why is that important? Okay, by the way, guys, I forgot to mention this. You know the angle at which it no longer leaves the glass block and it totally internally reflects? That is called the critical angle. Okay, so when it becomes to a critical angle, it means that the light will no longer leave the glass block. Okay, why is that important? Well, you can use it in optical fibers, and you can see that right here, and it works by exactly the same principle, total internal reflection. So the light source, which is shining in here, has been shone at such a steep angle that no light is then going to leave the glass block. All of it's going to be totally internally reflected back into it. Now, I've seen a load of these questions, and they usually involve a tube being drawn, and you have to show total internal reflection. If I were you, I'd just do it so the light goes in, and you just keep following. You know, remember a bit about reflection? That angle of incidence equals the angle of reflection. So whatever angle you shine it in, make sure it comes out the exact same angle. So that totally gets reflected, and that is reflected, and that is reflected. Okay. Also draw the arrows on that to show the direction of the light. Okay, those are all the things that you needed to do. This is probably like a 2 or 3 mark question, and it could not be easier. Okay, now analog and digital signals. Now this is an analog signal. That is like the old radio waves that you still get, which is what my car has. Okay, or TV signals. Okay, back in the day when I was growing up, I only had 5 channels. Okay, well, I actually only had 4 channels until Channel 5 came along. That was a very exciting time. Okay, but nowadays you guys have like your set-top boxes, and they use digital signals. Okay, now digital signals work by just this. Okay, so this will represent a 1, this will represent a 0, this will represent a 1, 0, 1, 0. Okay, and so your signal would be just a series of 1s and 0s, and your set-top box will then convert this back into another signal, which will take it back to a TV. So all the signals are transmitted in digital code. Okay, now that digital code is called binary code, and it's transmitted as 0s and 1s. You need to know, if it talks about 0s and 1s or shows you a wave like this, it's called binary code. Binary meaning numbers, so it's 0s and 1s. Digital signals are better than analog signals. Why? Because it can carry more information. Like I just said, that when I was a youngster, we used to only have analog waves, but the problem is, if you have so many waves in the air, you're going to get interference, okay, and you're going to lose the waves. So you can't have so many. You can only have so many waves traveling through the same airspace. But with digital signals, they don't really interfere with each other, and they can carry a lot more information. So they carry more information, and they do not suffer a loss in signals. For example, if there is a problem with this, and the images interfered with, the signal might come through looking like this, but the computer can still analyze that and know that this is still going to be a 1 and this is still going to be a 0, so you don't actually lose any information. Okay, so that is binary code. Morse code. Now Morse code is how probably some of your teachers probably used to communicate before mobile phones, only joking. And they're sent by flashes of light. Okay, now the benefits of Morse code is that it's quick because it goes at the speed of light, which is 300 million meters per second, very fast, and it can cover large distances and less errors. You're not going to make an error when you're just looking at the light. Now, this is Morse code. So this is like a dash. So for an A, it would just be like a very short flash and a longer flash. That would represent an A. But if it was a 0, it would be a long flash, long flash, long flash, long flash, long flash. Okay. If you were doing the letter T, you just do one long flash. Okay. If it was an N, one long flash and a very short flash, and that is Morse code. Okay. It can even be done with sound. So am I going to embarrass myself here? Why not? Okay. So for example, if it was going to be a D, it would be a D, D, D. Okay, that was going to be a D. If it was an E, it would be D. If it was going to be an F, it would be D, 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 D. That would be an F. Okay, you get the point. I've sufficiently embarrassed myself, but I'm going to move on to the next bit. Now, ghosting. This is about when you receive signals one directly after the other. Okay, so ghosting, what I mean by ghosting is that. Okay, so if you get a picture, you can see another shadowy picture behind it. Ghosting. Okay, now ghosting is caused by this. So for example, this is your house and this is your aerial. The aerial is going to transmit a signal directly to your house where you'll get your original picture right there. Okay, but you will receive 2 signals, because if you're near a tall building or a hill, the main signal is going to bounce off that tall building off the hill and then bounce back to your aerial, being delayed by a few seconds, and hence you will have the ghosting image that you get. Okay, now that is what is known as ghosting. Okay, now refraction of radio waves. You need to know that radio waves are refracted. Now you can see that when the frequency is very high, it shows very little refraction and the wave goes straight on. But you can see with the shorter frequencies, okay, with the lower frequency, it shows maximum diffraction. Okay, right. So that was right. So yeah, so that's that. But you can see how this one has the lower frequency, Okay, if it has a lower frequency, it has a higher wavelength. So the one with the lower frequency shows the most refraction, and it refracts so much that the radio wave returns back to Earth. Okay, but the one that has the higher frequency and the lower wavelength doesn't show as much refraction, and it leaves the atmosphere. This is the atmosphere, by the way, guys, the ionosphere. Okay, so that was refraction of radio waves. Right, DAB stands for Digital Audio Broadcasting. You need to know the advantages. Number 1, more radio stations. Number 2, less interference, so it's very clear. Number 3, you can choose radio stations by name as opposed to tune in the frequency, like for example Radio Derby is 104.5. Don't need to do that with DAB, we'll just go straight to Radio Derby. And disadvantages, you get some very poor coverage in some areas. That's one of the disadvantages. So disadvantages aren't so great if you're living in a good area. Okay, earthquakes. Okay, now earthquakes happen on fault lines, okay, which is the areas where the Earth's crust join up, and when those the tectonic plates rub together, they send shock waves through the Earth. Okay, now this can be measured by a seismograph, which is basically a string and a big iron ball with a pen on the end. So obviously, as the motion of the Earth moves, okay, due to the earthquake, the pen will move even more. You can see that right there. Okay, so it's a seismograph. Okay, now what you need to know is the focus of the earthquake is where it happens underneath the Earth's crust. So if the earthquake happens there, that is the focus. Okay, the epicenter of the earthquake is the part of the surface above the focus. So this is below the Earth's crust, which is the focus. Epicenter is the place right directly above the focus. Okay, so that's what it is. Now you need to know about P waves. P waves stands for primary waves, and they are transverse waves, and they travel through, okay, solids, okay, and liquids. Okay, S waves are secondary waves, okay, and they are longitudinal waves, okay, and they only travel through solids. I always think of it as S waves, solids, okay, P waves. P waves are just both, solids and liquids. And L waves are surface waves. Okay, the waves that go along the surface. So, that's a P wave, okay, and you can see that is basically just areas of compression. You can see the areas of compression, okay, those are the primary waves, and they, like I said, they go through solids and liquids, but this is an S wave, okay, which just goes through, like I said, solids, okay, and it's a transverse wave, so it goes up and down, up and down, up and down. Okay, so if you ever have to interpret one of these graphs, what you need to know is that P waves come first. Okay, then they're followed by the S waves over here, and then they're followed by the surface waves, otherwise known as L waves. Okay, so that's the order: PSS, PSS. Psst. Okay, I did that. Moving on, yeah, so no, this is showing exactly the same thing. Again, the first section shows the P wave, second section shows the S wave, and then the slightly more vigorous section is the L wave, surface wave. Okay, moving on to ozone. Everyone, right, okay, now I need to explain this to people because people always get confused with global warming and the hole in the ozone layer. Sorry, I think my battery on my laptop's running out. Bear me a second. Sorry, bear me a second. Oh, it is working. Okay, there we go. Right, sorry about that, guys. Battery is running out. Now, ozone. This is something that I do need to explain. Now, people always confuse the hole in the ozone layer, okay, to global warming somehow. I don't know how. Okay, but the hole in the ozone layer is literally a hole in the ozone layer. Now, we have a lot of UV radiation coming from the sun. Now, the layer of ozone is like a layer of atmosphere which blocks the UV radiation. Well, not blocks it, but absorbs some of it, so less harmful UV rays get in. But what we've been doing is we've been spraying gases called CFCs into the atmosphere from aerosol cans or refrigerators, and they made a massive hole in the ozone layer. Okay, and with that, harmful UV radiation from the sun can get through. Okay, so that's what that is. That's a hole in the ozone layer. Nothing, I repeat, nothing to do with global warming at all. Okay, so the ozone, hole in the ozone layer caused by CFCs from old aerosols and refrigerators. Okay, and you can see that hole in the ozone layer right there. Okay, now, coming to skin cancer, which is the last thing we're going to look at. Skin cancer, like I said, when people have a suntan, people are infatuated with suntans these days. Suntans is caused by the action of that UV radiation from the sun. Okay, now what happens is that UV radiation, okay, is absorbed by your skin, and there are cells which produce a pigment called melanin. Okay, now that melanin gives your skin the tanned appearance. Okay, now people with dark skin, okay, are less likely to tan and develop skin cancer, because that melanin, because the cells produce more melanin, it can absorb more UV radiation, so less UV radiation gets to the lower parts of the skin, which might become cancerous. So if someone is very, very light skinned, okay, and they don't tan, it means that they don't produce very much melanin, which means that UV radiation can really get absorbed into the skin and reach the lower parts, and you might have more of a chance of the skin cells turning cancerous. Whereas people with dark skin have more melanin, and so therefore that melanin absorbs the UV radiation and stops it reaching from the lower regions of the skin. Now, you can protect yourself by using sunscreen and covering up. Okay. Now, all suntan lotions have something called SPF in them. I know you've all seen that. Now, what SPF stands for is Sun Protection Factor. Now, the larger the SPF, the longer you can stay in the sun without being burned. Okay. Now, what weather forecasters they will do, they will give you, when it's the summertime, they will give you a sun index, which is a number ranging from 1 to 11. And what you do is multiply the time given by the sun index multiplied by the SPF factor, and that will give you the safe amount of time to stay in the sun. Let me explain what I mean by that. So SPF number, time given in the sun. So if you look at this, okay, let's imagine if they, on the news, they give, okay guys, you've got to be careful that the sun index, the UV index, is given at around about 8 to 10. Okay, that means that your burn time is going to be 20 minutes. This applies to light skin, by the way. Okay, not darker skin, but for light skin, the SPF, because people with light skin are most vulnerable to UV radiation. So if they give us an index of about 8 to 10, it means that you can only stay in the sun for about 20 minutes. Okay, that's the amount of time that you can stay in the sun before you begin to burn. Okay, now let's imagine if you're wearing a suntan lotion with an SPF factor of 10. That means that time given in the sun index, okay, for us it was 20 minutes. Okay, now let's imagine if you were wearing an SPF, okay, lotion of 10, okay, that would mean that would be the SPF number, which would be 10, multiplied by time in the index, which was 20 minutes, okay, so that would tell us that we now, with SPF 10, we can stay in the sun for 200 minutes, okay, that's what it would tell us. Okay. So that would be 200 minutes. Okay, and that was the end of the P1 revision video. So managed to do that in a little over 50 minutes. That's not too bad. So make sure you watch the other revision videos which will go over the exam papers, etc. Okay, alright, goodbye guys.